Hello, and welcome back to Intro to Cognitive Science. So, we are on a journey through the very beginnings of cognitive science as a field. Last time we talked about psychology and some philosophy, but the general idea of behaviorism, the movement that helped us turn away from sort of ill defined concepts of mental life and into the observable, which is good for science. Today, well, we also covered how that kind of broke down a bit. Today, we're going to cover a perhaps not exactly simultaneous, but a distinct and parallel advancement in the world of computing. In fact, the birth of the whole field of computing. So, let's get into it. Last time, again, we were finding a way towards a more scientific approach to the study of the mind and psychology by way of behaviorism. We were asking these questions about how behavior changes over time, right? Pavlov's dogs, Skinner's pigeons, classical conditioning. But we also talked about some roadblocks where we started to see findings that couldn't really be explained from a behaviorist perspective. There was evidence that even rats could pick up information from the environment that wasn't just related to a stimulus triggering them to have some new response, right? They learned places. We've also talked about language, how hierarchy can come into play. And, you know, these are ideas that we couldn't just explain with linear chains of stimulus-response pairs. So, we are getting into a place where we see the idea that the mind can do more than just take in and then spit out, take in information and spit out actions, right? It's doing something where it might be processing that information, holding on to it for later, keeping it for use, right? And so to really dig into this, if we want a field that explores more deeply how the mind does this kind of processing of information, we need a better theory of how information processing works in a mechanical way. Okay, so a big core question here is, how can something process information or perhaps execute functions or algorithms without a person involved? Now, I know we're talking about cognition and humans and brains and all these things. Of course, these are very human. But we need a better understanding. If we want to understand the way that the mechanisms of the human computational system might do things, we need to be able to explain it without having some person in the loop, right? How does any computation work? So, for example, we can learn explicit algorithms. We can learn tools, pen and paper, abacus, if we want to go way back. But human intuition and insight seem like they're kind of key to any problem solving, right? Well, this brings us to a philosophical tidbit that's worth discussing early and often. Have you heard of the homunculus? The homunculus, it's Latin for little man, and we can explain the idea of the homunculus here. A car doesn't drive itself, right? You see a car moving down the road, there's someone driving it, right? Okay, great. Someone is in the seat, hands on the wheel, feet on the pedals. Okay. But my hands aren't moving themselves. Who or what is moving my hands? Well, okay, come on. I know that my brain is involved here, so fine. My hands are part of my body, my brain is in charge. Oh, great, great, great. Okay, so if my brain is moving the hands, it's using the motor cortex to do that. Well, the motor cortex isn't activating itself. How, who or what or where is triggering the motor cortex to handle all of these motions involved in driving this car? The question goes on and on and on and on and on. At some point, if we're just doing this from sitting in our armchairs, we say, oh, there must be some little guy somewhere deep in my mind, right? Someone who is changing something, who is deciding things. This is a very big, very broad concept. It's useful for thinking about the idea that, hey, there must be some way, wherever this homunculus could possibly live, there's a whole lot of systems that work mechanically. If something is triggering my motor cortex works in some particular way. The question is, how does it work? Whether or not there's a little man somewhere guiding the whole process, we will leave for a deeper philosophical dive. But for now, the idea is there must be some way to physically represent computation, computing something. Where does my motor cortex tell my hand to move to make sure I don't hit the things on the road, right? So, let's get into a theory of how computation can be a physical thing. This started in pure mathematics. Mathematicians love to do this thing. They will pose challenges, open questions to the whole community to help figure out sought-after proofs of really difficult to describe problems. They'll have some money. It becomes a kind of a fun activity for a lot of them. So one of the big ones was the decision problem, the Entscheidungsproblem. If you're German, I probably didn't say that exactly right, but Germans love to just ram a bunch of words together to make full concepts. So the halting problem is related to this, which you might have heard of. Let's dig into this. The decision problem. Given any formal mathematical method M, there's some method, right? Is there some other method that can tell us whether that's actually solvable or not? Now, this is abstract. We're not going to dwell forever on how exactly this works. But the idea is, let's say I'm trying to launch a process on a whole lot of data, modern day computing problem, right? I might want to know if the thing I'm trying to do is solvable or not. Will it run forever, or will it actually ever be solvable? That would be nice, because then I could decide whether to keep going or stop, right? But to solve this one, there were some roadblocks involved. That it's sort of the idea that we are trying to find a method that analyzes the way another method works in math world. That was brand new. That was huge, right? How do we make a formal definition of how math works or how any algorithm works? We're a little more familiar with this stuff these days because some of us have had experience programming, writing scripts, messing around with computers, all this kind of stuff. But back then, back when everything was solved on pen and paper and humans were a huge part of the loop, this was mind-boggling. So, who comes in to start whacking away at this? Turing. You may have seen Benedict Cumberbatch, but Alan Turing. He was attempting to answer this, as many mathematicians do. And while he was doing this, and actually he discovered that decision problem is actually unsolvable, which is its own interesting finding. But along the way, he formalized the notions of what constitutes an algorithm and what constitutes computation of different functions, right? So he developed the concept of a computing machine, something that can solve or carry out algorithms in a predictable way that doesn't involve a human being having a hand on the reins. It's just machinery, a Turing machine. So Let's talk about what constitutes an algorithm in Turing world. An algorithm is a set of rules to be followed step by step to achieve some desired outcome that works every time. That's key. It'll always successfully do the thing, right? There's no question of it. So what's an example? How about a cooking recipe? You know, you go online, you find a recipe for making a certain kind of brownies or whatever. Yeah, you follow the rules, and sometimes you might need to account for things like elevation or whatever that change some of the properties. But this is all just step by step applied chemistry, right? Another algorithm that we've probably all a little more familiar with is long division. Oof. It's always kind of annoying. Everyone looks back on long division like, ugh, what an annoying time in algebra. Can't wait to get my calculator out. But it always works, right? It is a step-by-step process where you arrange the numbers vertically and you solve them out, one digit at a time, until you get the desired outcome correctly, every time. Making coffee is another one. Parallel parking. Some of you may be aghast. Oh my God, I hate parallel parking. It's always so confusing and inconsistent. But there's an algorithm to it. You may have seen this before, but as someone who has parallel parked quite a lot in my life and gotten some tickets for poorly doing it, there is an algorithm that will solve this problem. So, right spot. Like I said, not everyone does it right. Some people, I mean, I guess honestly they're not following all the rules, but they've executed the algorithm. In any case. Okay, so that's the concept of an algorithm. Something that we can execute every time and reach the end. Now let's talk about math functions. Now this was another piece of this. Turing turned the question of, can I algorithmatize things that classically aren't considered to be in that same way algorithmic. For instance, math functions, the inputs kind of just automatically become the outputs, and by way of some magic of human intuition, right? We were able to talk about the functions themselves, but not about the execution of the minute steps to achieve the functions. So, in math functions, inputs are numbers and outputs are a unique number for a given input, right? You may have heard this before. You're never going to put an input to the function in and get 3, 4, 5 different numbers out. You get one, right? That's a function. So, Turing was concerned with how do we map these sort of high-level function concepts from math onto lower-level algorithms, things that execute those functions. So what he ran with here is he wanted to find algorithms that calculate a mathematical function that can be specified in a finite number of steps, right? So they don't run infinitely. They are specified very, very tightly. Can be followed unambiguously. There's no confusion. There's no interpretation involved. You just define every single step, just like we did with the classic parallel parking. And it needs to always end up at the right result, right? It needs to always take the input and turn it into the output. So we got to get really specific here. What does it mean to specify an algorithm? And what does it mean to be unambiguous? These are so slippery. And I'm not asking you to be able to fully wrap your head around these. That's something that even the best mathematicians in the world less than a century ago couldn't do. But the idea is we have to really, really get specific if we want to make a system that does not get confused when executing any algorithm. So the Church-Turing thesis was the set of calculable mathematical functions are any functions that can be calculated by a Turing machine. What are they talking about? That's a strange way to phrase this. What the heck is a Turing machine? Aha! So this is the set of methods that Turing came up with to implement any algorithm. Okay, so the Turing machine. It is a hypothetical computing machine. That means you don't necessarily need to make this thing in reality to use it to help with these proofs, right? And the entire machine can be specified mathematically in simple mathematical steps. It's not necessarily a specific physical form. Like, you can make it out of anything you want. You could actually make one of these, apart from one small hitch, but you can physically create a Turing machine. So it has also, one of its major features, a machine table. And what that is that's what will specify the program and all the inputs and outputs so that you can execute the mathematical algorithm in question. Okay, cool. So what are we looking at here? This is a computing machine. It can be made kind of out of anything, and it carries out any algorithm you give to it. That should be familiar, because that's the dawn of all of computing, is this idea that I can create a system that I can feed any data that will then turn it into an algorithm and execute it. That's amazing, and that's what your phone is. That's whatever you're using to watch this right now is a Turing complete machine. It might also be familiar because it represents something else you use quite a lot. A computing machine can be made of anything, okay, or silicon chips or neurons, okay, and it carries out any algorithm you can give to it, provided it's specified well enough, right? Okay, so, we're drawing some connections here. So, what is the machine? Now, that to be clear, I'm not saying that the brain is exactly one Turing machine, but what I mean to say is that these concepts all align together, and this is how we're getting toward a field of cognitive science. So, the Turing machine. The Turing machine has a few features. It has a tape that is divided up into cells. This tape is infinitely long, so we don't have to talk about memory. We can have as much space as we need on this tape. Okay, so we're using the physical metaphor because this thing can exist physically. Great. So the tape, you have this infinite length of tape. You have a finite alphabet of symbols that you want to use. In the most simple case, this is just zeros and ones. You may have heard the computers work on zeros and ones. Interesting. Okay. It also has some kind of scanning item, something that can read and write to one cell. So it's able to take all the symbols that are on the tape, look at them, and then consult its internal table of instructions. So that it also has an internal state that can be changed, so it can keep track of some variables. And then the machine table itself has all of the instructions we need to carry out the thing. Okay. All right, let's actually look at it. So this is the model of a Turing machine. It has the infinite tape of where we will put information, where the machine will read information, where it will change information, and where it will ultimately leave the information in some form that has been solved, right, for the current algorithm. It can keep track of some kind of internal state, like what am I currently doing, and then it has a bunch of instructions on the machine table. Now let's talk about the machine table. The machine table has instructions. So these instructions will cause the Turing machine to produce one action at a time. Based on the input from the current cell, we will read the cell, right? And the machine's current internal state that will change in a few ways. We'll walk through examples, right? it can have these actions. I can either, the Turing machine, I can move left or right to a different cell. I can erase the symbol that's there. I can write a new symbol, whatever I want to do there. And then it can also change the internal state to something else. Okay, so looking back on it again, this is the way that this system will work. Is we'll load some kind of information onto the tape. We will put certain instructions in the machine table, and it's going to go through in one little chunk at a time, rearrange all of the information on the tape until it's in a different configuration. The input will algorithmically become the output. That's very big for math, because in math we think of solving complex mathematical functions based on things we've memorized. But this thing doesn't need memory. It has memory in the sense of it has a machine table to look up information on, and it has sort of an internal state that it keeps track of, but it doesn't need a human to do that. So, let's look at Turing machine instructions. Okay, so we have, each instruction is also kind of very, very rigorously defined. It has a start state, some kind of input that is read from the tape, some kind of action that the machine must take, and then an ending state. Sometimes the start and end state will be the same, and sometimes it will change. So if I am in start state and I can see the input, this is sort of the left hand checking, then I will execute the action and change my state to the end state. Okay, so we're getting from these high level algorithms to these like very low level, one little bit at a time checks and actions to take. Next, I have a little video that, it's good to hear it from multiple sources and multiple ways of phrasing it all. We'll watch this video about a Turing machine. There.
A major concern of early computer engineers, such as Alan Turing, was whether certain mathematical tasks were computable. To answer this question, Turing created the Turing Machine. What else would you call it? This hypothetical machine uses an infinitely long strip of tape composed of a series of cells with symbols written on them to store the inputs and outputs of computations. It also has a head that moves to the left or right that can read symbols from the cells, write symbols to the cells, and make decisions about what to do based on the contents of the cell and its current state. The state machine is essentially the program that tells the machine what tasks to perform. Every Turing machine must have a start or initial state. Based on the machine's state and the contents of the current cell of the strip, the machine will determine its next state, as indicated by the arrow called a state transition. The machine will also change the value in the current cell and may move the head to the left or right, or keep it in the same place. So, in the initial state, we see that the current cell has value 1. Our state diagram tells us that we will transition to state Q1, change the value of the current cell to a 0, and then move the head to the left 1 cell. Now we are in state Q1, and our current cell has value 0. Our state diagram tells us to transition to state Q2, change the current cell to 1, and keep the head in the same place. Now we're in state Q2, and our current cell has value 1. Our state diagram tells us to transition back to our initial state, change the current cell value to 1, which it already is, and move the head to the right. Finally, since our state is the initial state, and our current cell's value is 0, we transition to the halting state. Change the value in the cell to 0, and keep the head in the same place. The halt state is another critical state that every Turing machine needs. Without the halting state, the machine will keep looping forever and never complete its programmed task. Let's take a step back and
Actually, let's take a step back from the video. So, I hope that visually helps you keep following along with this concept, right? We have a system, it has an internal state, and it is reading information, changing information, and moving around on the information's space. Let's do some of these. So, let's write a little program that will scan the tape for the first one it finds, take it, and move it to the next 0 it finds. We can call this a leapfrog program. Very straightforward, but we can imagine this right now, right? We're gonna move left to right, so 0 is our start state here. That's where the head is currently positioned. We're gonna scan forward until we find the first one. We're gonna pick it up and drop it in the next 0. Okay, conceptually, broadly speaking, that all makes sense to us. We've already kind of solved it. Well, I know how I would do that. I'm a great big person, right? But we got to define this so that a machine can do it unambiguously and do it the same way every time. So let's write the machine table. Remember, we have a start state and an input value, and then we have an action to take and an ending state. Let's think about this. What do we first need? Well, we first need to go until we find a 1. Okay, so if we're in the state begin, here's our first instruction. If we're begin, we always start in begin. If we're in the state begin and our current input is 0, we're just going to move right and we're going to stay in the state begin. I'm not going to do anything until I find a 1, right? I'm just going to sweep the tape, move right, move right, move right until I reach a 1. Okay, now I found a 1. What do I do with it? Well, if I'm still in the begin state and I found a 1 finally, I'm going to write 0 and move right. And I'm going to change my state to leaping because we don't need to be in the begin state anymore. We've done everything we can do from the begin state. So now we're going to change our behavior based on the fact that, oh, hey, we've, quote, got the 1 now. And now we are leaping it over all the other 1s we find. Okay, great. So now, similarly, while we're in the leaping state, if we find a 1, we skip it. We don't care. We're not going to do anything with 1s. We're looking for the next 0 to drop this 1 into. So if we're in leaping and we see 1s, keep moving right. Stay in leaping. Okay, great. Finally, if we're in leaping and we finally find a 0, we now write the 1 and we change our state to done. So remember, the machine will always start in begin and terminate in done. Let's walk through executing this machine table. Okay, we start in state begin and we are looking at the first 0. Which instruction will fire? Take a beat, think about it. Based on the state, begin, and the current input, 0, that's instruction 1. All right, what's that going to do? It's going to move the machine head to the right. All right, cool. We're still in begin. Now let's look at the next element. Okay, so we're in begin and we're looking at a 1. Well, that's going to be instruction 2. Cool. Okay, so what is that going to do to us? That's going to write 0 where we are and move right. Great. And now we're in a new state. We're in leaping. So now we're leaping. We're on a 1. What does that mean? Leaping and 1, we're not going to do anything. We're just going to move. We're going to keep looking for our 0. So we stay in leaping. We call instruction 3. We stay in leaping. And now we are looking at our first 0 whilst in a leaping state. Heck yeah. Great. So we're leaping and looking at a 0. We write 1 and change our state to done. We have created a leapfrog program. Cool. Now, this is silly. This is not meant to be a powerful program, right? But it is meant to illustrate the idea that you have a high-level understanding of what this leapfrogging is supposed to do, and we have broken it down into the atomic information transformation steps required to actually execute it from a non-confusable, an uninterpretable way. This will always execute the exact same way. Fantastic. So, let's do another one. This time we'll describe it at the high level after we've gone through the low level. So let's look at this mystery functions machine table. So remember, start and input determine action and output in terms of states. So first instruction. If we're in begin and we see a 0, move right and stay in begin. Okay, seems a little familiar. We're going to do some kind of scanning. Okay. Begin 1. Well, in this case, we're going to write a 0 and we're going to move right into the state moving. Okay. This is very familiar. This is very much like the last one that we did. Okay, cool. So now we've run into a 1 and we flattened it. Okay. And we move to a new state. Okay, so now we're in another state. We're in moving. If we see 0s whilst in moving, we will continue to move right and stay in moving. Okay, this is similar to our begin, our instruction 1. It's just for a next state. Okay. Then finally, if we're in moving and we see a 1, write 0 and then done. Okay. So this has some things in common with the last one, but it's a little bit different. What is it doing? Well, let's walk through the steps to figure that out. So we start in state begin and we're looking at the 0 on the tape. All right. What's going to fire? Well, instruction 1, right? We're in begin and we're looking at nothing. So we're going to move right. Okay, cool. Now we're in begin and we're looking at a 1. What do? Well, we flatten it to a 0 and we move right. Okay, and we enter a new state, moving. Okay. So now we're in moving and we're looking at a 0. That's okay. We keep scanning, moving, looking at 0. Good. Instruction 3. We're in moving, we're looking at another 0. Okay, we're still going to call instruction 3. Okay. Now we're in moving and we're looking at a 1. Aha, moving 1, write 0, and we are done. What did this do? What was the function of this set of instructions? We started with a 0, 1, 0, 0, 1, 1, and we ended with a 0, 0, 0, 0, 0, 1. Conceptually, this isn't tied to anything very important, but we could describe this as a delete first 2 program. We have taken a string of 0s and 1s, and we have deleted the first 2 1s. Okay. We have changed fundamentally what that information is using this top to bottom process. All right, let's do one more. This one, I promise, will tie to something a little bit bigger. So, as usual, we want to look at the machine table for this thing. We are going to start with this 10011. We're in a begin state and we're looking at the first item. Okay, cool. So what's our set of machine instructions? We have begin 1, write 0, keep moving. Great. Begin 0, write 1, start moving. Okay. If we're moving and we see a 0, move right. Enter begin. If we're moving 1, move right, enter begin. Interesting. Okay, let's run this. We see a 1, and we're in begin. We're going to write 0 and enter the moving state. Okay. Now, we are in moving. We see a 0, move right, go back to begin. Okay, interesting. Okay, we're in begin. See a 0. Write 1 and with instruction 2. Okay, great. And we're in the moving state. So we'll move. We're looking at a 1. We'll move right and go back to the begin state. We may be seeing an issue here, but we'll keep going. So we see a 0. We're in begin. Change it to a 1. We're seeing a 1 while we're moving, move right, and go back to begin. Continue on, continue on, continue on. What have we done? two problems, two things here. One is a problem, and one is just an important point. So, first question is, what was this algorithm? What were we doing here? We went from a 10011 to a 01100. Now, this might not be familiar to everyone, but to some of you, you might notice this is an inversion. This is what's called logical knot. This is very useful. A 10011 getting knotted, the logical opposite, into 01100. Fantastic. This is a fundamental piece of how computers process information. This is how your computer works. A lot of kinds of storage use knots. You have to use knots a lot. I won't dig deeply into why. That's for a computer organization course if you ever take that. But for now, this idea is powerful. We have taken this very powerful binary operation, this logical process, and we've implemented it in a Turing machine. Now, what's the problem? That's the cool thing that we just did. Great. What's the problem? We forgot to have an end state, because this is just going to loop forever. You can see that from any time that we're in begin, we move to moving, and any time we're in moving, we move back to begin. We never stop. Oops. That would not be this would not be a halting program. Ugh. Oh well. But it still is a very important piece of how we can represent a higher level logical function, a binary knot, as a series of tiny steps. So this is the key concept, and this is kind of why we stop here in Turing world, is that a Turing machine takes a whole lot of tiny steps to convert an input to an output. With enough instructions and potential internal states, as represented by your machine table, you can simulate any mathematical function. I just showed you logical knot, or binary knot, the operator. That can help you build every other function in the world. It's one piece of the building blocks of other computations. So another key here is that those individual steps bear no meaningful resemblance whatsoever to the function that they produced. We weren't doing logical knot. We were looking at a thing and altering it one little tiny chunk at a time. But they still carry out the algorithm in an unambiguous way that cannot be confused by human or computer. This is big. This might also seem familiar because it parallels the concept of neurons. Think about neurons. You might not know much about them yet, and we'll talk more as we go forward, but the neuron is the fundamental biological mechanism for moving information around your body. In your brain, that makes a lot of sense, like, oh, okay, I'm processing some kind of visual input or something. But it's also your motor actions, the idea of should this muscle be firing or not, yes or no. And that's what a lot of neurons boil down to, is fire and don't fire, ones and zeros. They're all over your body, they activate your muscles, they process information, they do all kinds of complex cascades, like when you sneeze. That's a whole bunch of neurons all lining up to say, ooh, shoot, let's try to pull off this really weird maneuver that's good for the organism. Okay, here we go. So an individual neuron is quite simple. Well, that's not fair. They're very robust, interesting cells. But the way they function is conceptually simple. They're either firing or they're not. They're either doing the thing or they're not. Bears some resemblance to the binary information we were just working with. And they scale up. So neurons in networks, even though an individual neuron might be fairly simple, in conjunction, in big networks, they can simulate almost any function. And they do it in a way that doesn't really bear resemblance to the function itself. I'm not necessarily doing math when my neurons are solving the steps of math. That's a tough idea to wrap your head around, but it's key to understanding how we can look at minds as predictable, observable things. So, talk a little bit about universal Turing machines. So, because the way Turing has described any given Turing machine with any given Turing machine table, he can also build a universal Turing machine that is capable of executing any Turing machine's machine table. Oi, what does that mean? Well, the idea is I could load the tape up with instructions to store and execute. I could read machine table instructions from the data itself. Aha. So now there could be a Turing machine that can simulate every conceivable mathematical function, provided that we have a way of giving it inputs and outputs. So again, because a Turing machine is defined mathematically, we can define a Turing machine using another Turing machine to make all possible Turing machines. Why does that matter? Well, the idea that, an individual Turing machine is kind of stuck with its machine table, but if we can make one that is generalizable, we end up with modern computing. The CPU is the machine head. It takes keyboard, mouse, and internal information from disks, from RAM, as the tape, and it writes that information back out to the hard drive, to the monitor, to the speakers, all that good stuff. Your computer is doing this right now. This is how a Turing machine has changed the world, the concept of it. That we can feed digitized information to a universal Turing machine and have it do whatever the heck we want. Whether that's watch a lecture on a phone, or whether it is play video games on your PlayStation, it's all the same, right? This is all the moving of arbitrary information in some way that looks nothing like the final result. And that's pretty powerful. So, Turing demonstrates how you can create an information processing machine in the real world. You don't need human insight to process every possible algorithm as long as we can define it. So it's this purely algorithmic. There's no magic, there's no special insight or intuition needed. The tape cells and the machine table carry all the information, and you can process all of it purely mechanically. That's pretty important for understanding how we could get from neurons to minds. Does any given algorithm as well. So this is how the Turing machine helps to kind of defeat the need for a homunculus. It's also kind of a scary thought. Oh shoot, if there's no little guy in there, what am I? And that keeps coming up, doesn't it? So the mind could be thought of as a universal Turing machine. There's no little guy in there calling the shots. If we think of it as a universal Turing machine, then how do we kind of define the parts? Well, our machine table, our instructions, the things that we use to decide how to configure our inputs, read our inputs and turn them into meaningful outputs, that can come from biology, from memories, experiences, education, these kinds of things that we're doing every day here. And in a certain light, we could just be a neurologically realized system for moving information around in an intelligent way. That can be tricky. It's a little disconcerting to think of myself as no more than a mechanical set of clockwork. But it's okay. Remember, cogito ergo sum. I think, therefore, I must at least exist. Whether or not I'm fully predictable, okay, we'll dig in. So, to review, Turing introduced this concept of a physically plausible machine designed to compute anything. Accidentally, along the way, revolutionized the whole concept of modern computing. and helped build cognitive science and artificial intelligence and all these other amazing things that come from the idea that information moving around might be describable, and our cognition might just be one flavor of all of that. So, this gives way to the, broadly speaking, the information processing model of the human mind. Okay. Final thought. Think of some process you do in a given day, and then break it down into the most basic step-by-step instructions that you can possibly think of. All right. Take care.